All right, so real quick, I want to talk about something like what we have, and I messed this up here in my notes. When you have AC circuits with sources that have different frequencies, all right, the process basically is that you got to do superposition for this type of analysis. And the issue, like I'll take this example here, right? I've got two current sources and a inductor that they're in parallel with. All right. So if I asked you what is I3, you should know what I3 is just from looking at this. But I don't need to know any kind of phasors. What is it? Yeah. I3 is I1 plus I2. Now that would end up being 3 cosine 10t plus 30 degrees plus 4 cosine 100t plus 40 degrees. All right. There's no way I can convert that to a phasor. Right? To have a phasor, I have to have one frequency. All right. So how do I approach this sort of thing? Well, I have no choice but to use superposition. All right. And so basically my approach, I don't know what I was thinking here when I did this, but basically solve for the desired phasor at each frequency, right? And then basically do all of your analysis in the phasor domain and then convert everything back and add them up, okay? So what I would do here is I would say to myself, all right, well, what's the phasor that I would have that goes with I1? This guy would be I1 equals 3 angle 30. So what have I stripped out of that? I said there's three parameters that define a cosine at any given time, right? The three parameters are what? Magnitude, angle, and frequency, right? What have I stripped out? I stripped out the frequency. So the frequency is out of the picture. You are directly implying that all of your analysis is going to be at one individual frequency at that point. Now here's a question like you have on the homework. What's the frequency at DC if I have a DC source? 0, right? The period of DC is infinite, right? It takes an infinite amount of time for it to repeat, right? Effectively, it's never really changing, right? So its frequency is 0. All right, so if I had that, when I have DC, 1 over j omega c, think about that for a second. At DC, omega is 0. What's the impedance? What's that? Infinite, which is a what? An infinite impedance is a what? Open circuit, right? That kind of makes sense. That jives with what we did in first order circuits, right? In first order circuits, we said in steady state, what's a capacitor? An open, right? And we were talking about what kinds of sources when we did first order circuits and second order circuits. What was DC sources, right? So steady state, we were doing steady state. When we're doing impedance, we're doing steady state, all right? And I can think of a DC source as an AC source with 0 frequency, right? Because it's not changing. All right, so that's something we talk about pretty frequently. So if I had a DC source, I'd go through all the same approach, right? In fact, you've been doing impedance analysis at some level when you did first and second order circuits, when you did the steady state analysis, and you were using impedance without actually calling it that, okay? All right. What about I2? What's its phasor? 4 angle 40. Okay. Now, if I wanted to figure out what the result is here, I'd have to use superposition. Basically, what I'd have to do here is I would have to say, so I want to figure out the voltage V of t. I want to figure out what the voltage is across there. So what I would do is I would say, using superposition, I would do my analysis with I1 on, and then I would turn I2 off. So if I do I2 off, what's that do to the current source if it's off? It's an open, right? 0 current is an open circuit, right? So I have this, and I would call this V1, like that. And I would say this impedance here, this guy would be J, what would that be? How would I write the impedance of that inductor? Omega L, and what's my omega here? 10. All right, this guy would be J10, and I'm probably gonna run out of space. I'm gonna call it L, and my L is 100 microfarad. All right. Now, the other circuit would be this one. Same circuit, really, except this is I2. Like that. All right, and this is V2. What's the impedance here? J100L, right? J100L. So I would do my analysis, and then the voltage across this thing would be what? How would what's the voltage phasor ultimately across that inductor? It's V1 plus V2, except they're each at different frequencies. So what I have to do is I got to transform this phasor back into the time domain. And then I got to transform this phasor back into the time domain and add them. Okay. So in this case, what I would say is I have, if I do that math, V1 and V2, all right, from the previous slide, I end up with 3 millivolts, 0.003, angle 120. And this one is 0.04, angle 130. Like that, if I did that analysis. Okay. So the question then would be, what would be V of t? What would be the voltage there?
Back to rectangle and come together.
Not convert. I don't need to. In fact, I don't want to convert them back to rectangular, right? I guess I could in some ways, and then I'd have a different form for my answer. But if I'm in the time domain, I want to put it in that cosine with an angle form, right? So how do I get 0.003 angle 120 into the right form? This is an important step because again, I wish we had a lab. We don't have a lab that goes. I mean, you do have a. I watch my mouth when I'm recording this. I wish I could control your lab and what you're doing there, and it was exactly like what we're talking about here, but I don't. Important thing is that in the real world, you build a circuit, and a circuit has sine waves that are going through it, and we use phasors just to do the analysis. Okay, so it's important to understand that relationship between the phasor and the actual sine wave. So how do I get this V of t? It's the phasor of V1 plus the phasor of V2, but I have to remember that I take their frequencies into account. So what do I do for V1? Do something. How do I convert back to the time domain? Forget the V2 exists. Just think about V1 by itself. So so when I had 3 cosine 10t plus 30 degrees, I converted that to 3 angle 30. So if I had to reverse convert that, what do I do?
So just be 0.003 cosine 10t.
Yes, it would be 0.003, the amplitude of that cosine wave. The frequency would be 10t because this guy had a frequency of 10, right? Plus 120 degrees. Right? Again, the whole idea of the phasor is it just strips out the whole this frequency times t term, which if I have frequency times t, it means differential equations, it means calculus. Right? We go back to algebra using the complex numbers. That's the whole reason why we do it. All right. Now this result gets added to whatever I get from the other term, right? This guy had a frequency of omega equal to 100. A lab would help you to see this better, right? Probably if we did this with a lab. What would I put for the other one? If the frequency is 100. Yeah. So 0.04 cosine 100t plus 130. All right, that's the basic approach for this. So if you looked at that on an oscilloscope, it would look a little bit funny because it would have 2 different frequencies in it. All right, but there's no way on an oscilloscope or whatever in the real world to do the analysis in the phasor domain. Okay, so we do it like this. Now you'll learn some tools in 2254 and 3111 called the Fourier transform. It kind of allows you to do this. All right. it doesn't kind of, it allows you to do it. But it's the frequency domain or the phasor domain is an imaginary place where we do our analysis. All right, the real world, if you look at voltages and currents, they're sinusoidal. Okay. All right, so we're going to use superposition now for some analysis, but not at different frequencies. All right, what I'm going to do now is I want to use superposition. I want to get a Norton equivalent circuit looking into the terminals here. And what do I mean when I say Norton equivalent circuit? What is it? Well, it's a Thevenin equivalent circuit with a source transformation, right? So what would it look like? Yeah. Yeah. Current source in parallel with whatever impedance Z Thevenin I have. And the voltage I would see right there would be the open circuit voltage. What's this current? Well, the current here is 0, yeah. But what's that current source? In a Norton equivalent circuit, it's the short circuit current. All right. And the voltage I would measure across the terminals would be the open circuit voltage. This guy is entirely equivalent to a Thevenin equivalent. And you see the source transformation would tell you that, right? You would see that the source transformation would tell you that ISC times Z Thevenin is V open circuit. That Z Thevenin, I've talked about this a lot now. That Z Thevenin, that's the impedance that's seen by what source? The load source. So if I connected a source across the terminals, Z Thevenin would be the impedance seen by that source. And it's the impedance seen by that source, meaning what we do is we turn off all of the sources inside the network and say only basically what is the load current doing? What impedance does it see? What voltage would it create if I had that current source there? All right. So for me now, what do I want to do? Well, I've got probably not the way you want to do it. If you saw this, I have a feeling a lot of you guys would say, let's do mesh analysis, right? I think that's probably a solid way to look at this. I have no problems with mesh and nodal, right? I don't, but they're not all that particularly convenient, I don't think. Particularly when you get into electronics and the way that people look at circuits and electronics. I also just want to get you guys comfortable with other methods, and I know you choose not to use the other ones, right? And in part because my theory is that you learn the equivalent circuit stuff first in 2111, and then you learn Thevenin and Norton, or you learn nodal and mesh later, and you're better at that point. So you just get more comfortable with those. All right, so my job is to make you aware of the whole thing. All right, so we're not going to use mesh or nodal, but mesh or nodal are probably fine. So if I'm going to do it the way that I want to propose to do it, to exercise this a little bit, I'm going to use superposition. So if I do superposition, how do I do it here? What do I need to do? Do one source to start with. And basically the process is I find the phasor for the short circuit current in 2 steps. Right. Basically what I do is I find the component that's caused by the 6-volt source. I find the component that's caused by the 4-amp source, and then I add them together. All right. So when I do this, then if I'm looking specifically for the short circuit current, that means that I gotta put a short across there. So this is why part of the reason why I don't like mesh and nodal, and I don't like them. There's nothing wrong with them, but I don't want to do it if I don't have to. Part of the reason is, how many meshes do I have here? 4, and I have 3 that I have to solve for, right? You should see that I've got 1 that's a given. I don't like having to go to matrices and things like that, right? Because for me, then I get to numbers. I don't like numbers. I'd rather just see the results if I can, and just see it symbolically. And that's how I'm going to approach this guy here. All right. So the first step is, I think the way I labeled it, step 1A for me is I just want to do the 6-volt source, then the 4-amp, right? So if I turn off the 4-amp source, what do I do with it when I turn it off? Open circuit. So, all right, so that means that I'm going to turn this circuit into, I'll call this, so this guy is simply, he's 6 volts with an angle of 0. So I'm just going to make him 6 volts. This guy's negative J. This guy's 1. This guy's J. What about the 1 ohm down there? Do I keep it? I sure do, right? But I get rid of the current source. So that whole branch with the current source. And I got another 1 ohm. Got another 1 ohm. I think that's all the 1 ohms in it. And I got a short. All right, now, my job ultimately is going to be to find, I guess in this circuit, I'm going to call it, call this ISC 6 volts. All right, I want to find that current. Okay. All right, where do I start? I want to simplify this down to a single circuit. In other words, I want to get a 6-volt source in series with a single impedance. So where do I begin with that process? Got a 1 ohm resistor in parallel with a short. How do you know they're in parallel? Well, if I do a KVL around that loop, right? It's got the same voltage. And the voltage across the 1 ohm is what? 0. So how much current goes through that? Nothing goes through the resistor. All of it's going to go through that 0 ohms, right? Okay. And the reason why all of it goes, the thing is, the reason why all of it goes through the 0 ohms is because the voltage across the resistor is 0. When the voltage across the resistor is 0, the current through it is 0. All right, always think in terms of KVL and Ohm's law, right? All right, so we're going to simplify that down. That guy becomes, I'm going to simplify it slow. All right, so I got my 6 ohm, or my 6 volts, my minus J, my 1 ohm. I've got J down here. Got my 1 ohm. Got my 1 ohm. My 1 ohm. And that. Okay. Now, basically I get rid of one of the 1 ohm resistors. What's the next simplification that I see here? Is 2, yeah. 1 plus 1 is 2, right? So I got 1 and 1 in series with each other, right? The 1 ohm and the 1 ohm are in series with each other. Why? Because they've got the same current through them. All right, so I don't want to spend forever redrawing this thing, so I'm going to make this 2, like that. What would be the next simplification? 2 in parallel with 1, right? Then I've got this into one equivalent circuit. So I say that this guy becomes 6 volts, negative J, 1 single resistor, and then J. And this guy becomes 1 in parallel with 2, whatever number that may be. I think that's going to be 2/3. Okay. If I looked at what's the total equivalent impedance here? What is that? What would the total equivalent impedance here be? 2/3, right? Because what do I have? I have negative J plus J plus 2/3. So this guy, the total impedance would just be 2/3. Negative J and plus J would cancel each other, right? So the total current I end up with here would be, if I go through that math, I think this current, so what do I call this? I don't know, I'll call it I6 because it's the current through the 6-volt source. This would work out to be, if I do the math on this whole thing, it would work out to be 9 amps. All right. And just to be clear, that guy is basically 6 divided by negative J plus 1 in parallel with 2. Okay, that's where I would work out that to be 9 amps. Is that the current I wanted to find? No, it's not. Where is it back in the original circuit? Well, the original circuit really is not this top one. I mean, I guess this is the original circuit, but the original circuit we were looking at was the bottom one here. So I6 is here. All right. So I could do a current divider, all right? And specifically the current divider that I'd be looking at, really, I guess I want to look at it in terms of this circuit, maybe. Call this I6. I know the current going into a parallel combination of stuff, all right? This guy here is the short circuit current. This is I short circuit 6 V. How do I know that? How do I know that's the, I said, all right, that's the current here. How do I know that that's also there? Well, right here at this particular point, right? This is, I'm saying this current here and this current here are the same. How do I know that those two currents are the same? So the current in this 1 ohm resistor here and this branch here, why do I know they're the same? None of the current goes through that 1 ohm resistor, right? So I know that those two currents have to be the same, right? And I know that this simplified circuit here was essentially, I took everything basically to the left of that dashed line that I just drew. Everything to the left of that dashed line was replaced with the 2 ohm resistor, right? Actually, it's, to be clear, I guess the dashed line is really, should be, I'll draw it as a non-dashed line. It should be right there. That arc would be the dividing line, right? So everything to the left of this arc, sorry, everything to the right of that arc is a 2 ohm resistance, right? They're equivalent to each other. So that means the current entering both here and here has to be the same, all right? That's what makes them equivalent circuits. The currents are the same. All right, so if I wanted to find that current, ISC 6 volts, how would I find that? All right, so I6 is the current I know. It's going into a parallel combination of stuff. What's my approach for figuring out what the current is there in an individual branch when I got 2 branches in parallel? How do I use that current divider approach? I find the voltage, and then what? To find the current in an individual branch, if I have 2 branches in parallel, I know the current going into the parallel combination. What do? I find the voltage, then I find the current in the branch. How do I find the voltage in a parallel combination? Yeah, and the impedance here basically would be, so it's I6, that's the current that's entering here, right? This is I6. All right. I6 times 1 in parallel with 2. Let me make that clearer. 1 in parallel with 2. That's the voltage across that. And then to find the current, I divide by an impedance. Which impedance? The 2 ohms. All right. And if I do that, I work out to 3 amps. And technically, that's with an angle of 0 degrees. All right. It is sinusoidal after all. All right. It's just to say that there's no angle or a 0 degree angle. Okay. Questions about how I went through that process? Yeah. Which last? How I did this? Yeah, so what I did was I said, so just to branch it out for a second, what I said was, I have 1 ohms and 2 ohms in parallel. I know that the current entering here is I6. All right, so if I want to find this current right here, I short circuit 6 volts is what I called it. What I say is the voltage across that thing, V, has to be I6 times 1 in parallel with 2. right? That's just to say, okay, if I know the current entering that combination, I know the impedance, it's just I times R. And then if I want to find what's I short circuit 6 volts, that's the current in that 2 ohm branch. So basically I take V and divide it by 2. Right? That's my basic approach. I don't like formulas, right? I like just thinking in terms of Ohm's law and KVL and KCL. Right? So I'll always kind of think of it that way. And that works out to be 3 amps. Okay. All right. Now I have the other approach I got to take. So I got to figure out what's going on with we did the 6 volt source. So now we got to do the 4 amp source. So how do I do that? How do I do the 4 amp source? What's the first thing I got to do? Turn off the voltage source. Yeah, so if I turn off the voltage source, what do I do with it? I short it, make it 0 volts. Okay, so 0 volts, any current. So comes a short. This guy's negative J. This guy's 1 ohm. See, this is J. I got my 4 amps down here. Got my 1 ohm. And then I got another 1 ohm. Got another 1 ohm. I guess the other thing I wanted to make clear here is we are doing the short circuit current. There's also a short there. So there's another branch here, like that. And this is the current I'm looking for. I'm looking for I short circuit 4 amps. We call it that. All right. So again, I want to start my simplifications and I want to get it down to basically one impedance that's seen facing this 4 amp current source. So where do I start again? Where do I start my simplification? If I'm trying to find the impedance that's facing this 4 amps, I always start as far away from the 4 amp source as I can. And then I collapse it down, right? So where do I start?
Rid of the 1 ohm.
Get rid of the 1 ohm. We got a couple of 1 ohms, but I think I know the one you mean. Yeah, the one at the far right. Why get rid of that one?
Parallel with it.
It's in parallel with the short circuit. 0 volts across the resistor means there's no current in the resistor. All right, so this guy goes to a short. So that's going to turn this into, here's negative J. Here's 1. Here's J. Here's a 4 amp source. There's another 1 ohm. And then another 1 ohm. And the other 1 ohm is gone. Now, what do I do? Where should I go from here? I can't simplify that any further. I don't know any way to simplify that. What's in parallel here? Do I have any clear parallel combinations of things that I can do? Not really, right? If I look at this, the 1 ohm, the 1 ohm on the far right here, this guy, he's in parallel with stuff, right? What's he in parallel with? He's kind of in parallel with the 1 ohm, the other 2 1 ohms, kind of, but not really, right? Why not? Why do I say not really? There's like 3 nodes right here, right? So if I look at this, like there's no clear place where I can break. To use that approach of equivalent circuits, I have to be able to break at a port where I have 2 terminals coming out. I don't have that here, right? So in other words, there's a node here where current would enter. There's a node here. There's a node here. There's no clear way. There's nothing that I can see here that I can further simplify this guy, right? Technically, the J and the 1 are in parallel with the negative J. But again, in the middle, I've got this breakout. So there's nothing that's really going to help me, right? So there was like, it's not true that the 4 amp current that is here would leave here, because some of it's going to go this way too, right? So I got no clear way to go any further with this. All right. This is not the kind of test, kind of problem, unless I was really working, this is probably a little bit more difficult than I would expect to do on a test, where I would say do superposition with this thing. This is probably something that would be easier with mesh. I totally agree with that. I'm doing this to exercise your brain, because you guys just need to learn. If I keep doing the things you're comfortable with, you're not gonna learn. All right, so I'm trying to just push your horizons a little bit with this, but to do this with superposition is probably not the most efficient use of your time. All right, but it really is just a methodology for me to make sure you guys are learning all the methodologies. Okay. All right. Given that I painted myself in this corner, what do I do now? I could do mesh analysis, but again, I'm going to keep going with my usual sort of approach of what I'm going to do is say I'm going to do the approach now of creating a Thevenin equivalent. And I'm going to say I want to turn this into a V open circuit sum Z equivalent. And then I'm going to hang at the terminals a 1 ohm resistor. So in other words, basically right here and right here, across that plane, I'm going to break the circuit. Okay. And I'm going to try to find at that point, everything looking to the left of that plane, right, left of that line, I'm going to try to make a Thevenin equivalent. All right. And then I'm going to hang the 1 ohm on there. And then from hanging that 1 ohm on there, I'm going to be able to figure out what to do. All right. You guys with me? That current, just to be clear, right? So we don't have to go back through this argument again. The I short circuit 4 amps is also the current here, right? Right? Because I know how much current flows through this 1 ohm resistor. 0, right? The 1 ohm resistor that we're talking about here is that 1 ohm resistor. All right. So that means that this current here is I short circuit 4 amps. So this current is I short circuit 4 amps. Okay. So I just got to find that Thevenin equivalent now, drop, and then use this approach to make the simplification. So in other words, at this point, what I'm doing is I have negative J 1 J 4 amps. The 1 ohm. All right, this is my approach here. So I'm going to call these terminals, I guess I'm going to call them A and B. Call this A, call this B. All right, so how am I going to approach that? Say that again. I took the 1 ohm off because I said I want to find a Thevenin equivalent looking to the left of that line. Okay, so what do I do now? Can I start combining impedances? I can start combining impedances here. Yeah, so how do I start combining those impedances here? Yeah, well, if I'm thinking about finding the open circuit voltage here, first thing is, what do I want to find? If I'm turning this guy into a Thevenin equivalent, I want to find the open circuit voltage. So I want to find this guy here, VOC. How much current flows into here? How much current's flowing here? None. All right, none. So in that case, I do have a parallel combination. So previously I didn't have a parallel combination. Now I do. All right, that's why I like this circuit. It gets us thinking, right? So where's the parallel combination that I have now? I actually do have a parallel combination of stuff. Not the J and the 1 minus J. Let's say if I draw it like this, I have the 4 amps. All right. That guy shoots his current up. I'll think of it this way. He shoots his current up into this and into the other branch. So I can look at it like this. For me, I see that I have negative J and the 1 ohm in series with each other. And then I have the J in parallel with those two. And then that combination goes into a 1 ohm resistor. Now, that was a weird redrawing. But if you're not asleep, your head's probably exploding on it, right? So what did I do? How was I able to do this? So I'm saying that the 4 amp and the 1 ohm are in series with each other. Okay, it's just these branches might throw us off. I'm gonna take those branches off there, right? Because maybe that'll help. Now I can see here that the 4 amp and the 1 ohm are in series, right? Because they both have 4 amps through them. The 4 amps, when it gets to this node right here, right, it splits 2 ways. Part of that current goes into the negative J and the 1 ohm in series with each other. And then part of it goes into the J, right? So what I could do, the thinking then for that type of approach is I break the circuit at this point, like that, right? And I can say that in looking at breaking the circuit at that point, I can say that I have a J, so a negative J and a 1 in series. That combination is in parallel with J. I can replace that with 1 impedance, which is clearly in series with the other stuff down here. When I'm using this equivalent circuit approach, I'm always breaking at a set of terminals and saying, okay, what's equivalent on the other side of those terminals? And then making the replacement of the equivalent impedance. That's the basic approach that we always follow in this approach. Questions about that? All right. It's a pretty tough looking circuit, I think, for most people to sort of think through. All right. So at this point, what I would do is I would try to solve this. And again, this is me really pushing hard here to try to figure out how to go through this kind of thing. Right. So if I wanted to solve this, just to remind ourselves, what the heck am I looking for? I wanted to find this voltage right here. Right? Mesh analysis would have been easier for sure. Right. What do I want to find for myself? Well, VOC, just a quick look here. VOC is equal to what? VA minus VB. What do you mean by that? Well, if I labeled those nodes, right? So basically, if I did a KVL, it's whatever, I guess I'll call this V1, and I'll call this V2. VOC, if I did a KVL, is V1 plus V2. Okay. I know what V2 is already, don't I? It's 4 volts. How do I know it's 4 volts? Because I know the current going through it, right? I've got 4 amps that's going this way through that loop, right? So that's got to be 4 volts. So what do I got to find? I got to find V1. Where's V1? Well, V1 is the voltage across that 1 ohm resistor right there, which means I got to find the current through this branch here. So how would I find the current through that branch? I'm going to do a current divider, right? And so how do I approach that? So I'm going to call this guy I1 right here. I1, how would I find that? I know the current going into a parallel combination of things, right? So what do? I say it's the voltage across that parallel combination of things, right? What's the voltage across that parallel combination of things? Well, it's 1 ohm minus J so 1 ohm minus J in parallel with J, right? Times 4 amps. That's the voltage across that combination of things. If I divide that by 1 minus J, that will be the current in that branch. If I wanted to find V1, which is the voltage across that resistor, it would be 1 ohm times I1. Okay. What I would do at this point is I would say, well, VOC has to be equal to V1 plus V2. That's going to be a number. All right. I'm not going to simplify it any further. You might want to watch the video on this one to make sure you can follow everything I just did. So the other thing I got to do is I got to say, okay, well, what's the Thevenin equivalent impedance looking into that network, right? So I had minus J, I had 1 ohm, and if I'm finding a Thevenin equivalent impedance, I turn off the current source. What is the equivalent impedance ZEQ looking into this network? There is. Yeah, thank you. What's the Thevenin equivalent impedance looking into this network? Well, going into this network, it looks like, simplifying from the back, I see that the J and the minus J are in series. J plus minus J is what? 0. So basically what I have is this guy becomes 1 ohm short circuit, 1 ohm, like that. What's my ZEQ? 1 ohm. All right. My ZEQ becomes 1 ohm. And so basically what I did was I said, all right, I simplified this whole thing down into this VOC and this ZEQ, right? So I made that circuit. Now the thing that I was doing was I was trying to make that circuit, and I was going to slap this 1 ohm back on there to try to figure out what was the current in that network. So I do that. Slap that 1 ohm back on there. And I want to find this current, which is I short circuit 6 amps, or sorry, 4 amps. All right. Which would be what, based on what I just showed right there? I short circuit 4 amps would be what? Yeah, VOC. Yeah, it's going to be divided by 2. I'll say ZEQ plus 1, which is going to be 2. Okay. Now I have I short circuit 4 amps, and I have, if I do the math on this, this guy works out to be 2 plus J2. All right, 2 plus J2. So the actual I short circuit current that I end up with here, the I short circuit current I end up with is the sum of those two currents. So I short circuit 6 volts, short circuit 6 volts, plus I short circuit 4 amps. That guy's going to become 5.3852 with an angle of 21.8 degrees, if you do the math. All right. Now there's still I was trying to find a Norton equivalent circuit. That's what I started about a half an hour ago, right? What would it be? Well, the last part I have to do is find Z7, right? Find Z7, and what would I do? Turn off the sources and then combine all the impedances, right? So we'd go through that process. I'm going to stop there, and you guys should be able to figure that part out.